In this video, we are going to discuss more information pertaining to trig integrals, specifically address examples of trig integrals. The first video pertaining to trig integrals gave a basic introduction of the breakdown for the section into 5 Roman numerals. It also discussed the formula sheet and the tables and the blue boxes and the formulas that are already established. In this video, I will give examples of problems that you may see on quizzes or on your major test. And with those examples, I will show you how the formula sheet is very helpful and how to use the tables and the blue box formulas. Before I begin with anything too specific, I did refer to this last page of blue box specials. The antiderivative of cotangent u quantity cubed and the antiderivative of cosecant u. I wish to show you how those two formulas are derived. You will never have to derive those for me, but you will be able to, or I will ask you to, on a test or a quiz. For example, I think we discussed this in the last video. I could ask you to integrate the cotangent of 5x plus 7 quantity cubed. And after u substitution, when you change everything over to u, you would be able to use the blue box formula, and then you would go back to x by letting u be 5x plus 7. So your final answer would be in terms of x. You would not have to derive the formula, but after u sub, you would use the formula. I want to show you how they derived the formula for cotangent cubed, and that is here. And it's a short little proof. What they did is, if you notice, they did not give a reduction formula for cotangent to the power of n. They gave a reduction formula of tangent to the power of n, specifically tangent cubed, but they did not give a reduction formula for cotangent cubed. So the blue box special can be proven with an alternative method, which is kind of like Roman numeral number 5, alternative methods when we don't have our reduction formulas, or we wish to not use reduction formulas. So the technique is to split off a factor of cotangent. So this is still cotangent cubed. For cotangent squared by the Pythagorean identity, we know that it's equivalent to cosecant squared x minus 1, and then multiply by cotangent. With this, what we will do next is we will distribute cosecant squared x times cotangent x and negative 1 times cotangent x. Then it is broken into two indefinite integrals. This first one, cosecant squared times cotangent, I wrote as cotangent times cosecant squared. It's okay to do that. Multiplication is commutative. This second one is one of your blue box specials. And I'll remind you, the blue box special for cotangent is natural log absolute value of sine u plus c. Now, we need u sub for this particular indefinite integral, and we can do that by letting u be cotangent x, and from our basic trig days and calculus 1 days, we know its derivative is negative cosecant squared. Therefore, I put a negative on the inside and on the outside, which is a positive 1 or a form of 1, and this becomes negative antiderivative of u with respect to u. And where you see me have minus the natural log absolute value of sine x, that is the blue box special. So minus, if we go from the antiderivative of cotangent to this, that's the blue box formula for cotangent x. it is natural log absolute value of sine x. The minus is here because we broke it up into two indefinite integrals and there was subtraction here. So there's subtraction here and there's subtraction here. But the blue box part of it for cotangent is just the natural log absolute value of sine x. And I said plus a c sub 1, and that's going to come into play in just a moment. And I say c sub 1 mainly because we've not finished this indefinite integral, which you know is going to be negative 1/2 u squared minus the natural log absolute value of sine x plus c. Then going all the way back to x, u is cotangent x, so this is negative 1/2 cotangent squared x minus natural log absolute value of sine x plus c sub 1. And what you're about to see, technically, you could say that's the blue box formula, but if you look on your formula sheet, that's not the preferred form of the formula they would like for you to use. The blue box special is in terms of cosecant just by itself, and that's the form they wish for you to use. But do know that this technically, at this stage, you would be done. It just involves a cotangent and sine. So in order to go all the way back to cosecant, we use the Pythagorean identity once again, that cotangent squared is cosecant squared x minus 1 minus natural log absolute value of sine x plus c sub 1. And then I distribute my negative 1/2, so negative 1/2 cosecant squared plus 1/2 minus natural log absolute value of sine x plus c1. And then I have the negative 1/2 cosecant squared x minus natural log absolute value of sine x plus c. What happens with the 1/2 and the c sub 1 is when I add c1 and 1/2 together, because that's addition there, 1/2 plus c sub 1 is equal to c, the overall constant of integration. So I would combine these or add these two together to get an overall plus c. And I think you know how we go from a negative natural log absolute value of sine x to a positive natural log absolute value of cosecant x. We would take this negative 1, and then we would make the exponent negative 1 here. Sine of x raised to the negative 1 power is 1 over sine x, which is cosecant x. And hence, there's the blue box special for cotangent cubed x, and it's on the formula sheet. Now, would I ever expect you to derive this formula again? No, but you may have to utilize this blue box special for other types of problems. And I think we discussed that for this type of problem, where u is 5x plus 7. So once you go and change everything over to u and it becomes cotangent u quantity cubed, you could go to your blue box special and then finally go back to x. So that's the proof of cotangent cube. Remember, the textbook or the insert did not have a reduction formula. There are formulas out there. I want to show you what the insert says in particular about this. It's kind of like a footnote or a note off to the side. It is located here at the 5th Roman numeral. It says, with the aid of the identity that 1 plus cotangent squared equals cosecant squared, the techniques in table 7.3.2 can be adapted to evaluate integrals of the form cotangent to the power of m times cosecant to the power of n. It is also possible to derive reduction formulas for powers of cotangent and cosecant that are the same or very similar to the formulas that we have here. So this particular section does not concentrate heavily on reduction formulas for cotangent and cosecant. It does not focus on, it says here, the table can be adapted to evaluate integrals which involve products of cotangent and cosecant. The section deals with products of tangent and secant with a table, and it deals with reduction formulas with powers of tangent and powers of secant, but it does not give anything in regards to cotangent and cosecant. Just know that it does say there are reduction formulas out there for these types of situations. And there are also tables for this type of situation. They're just not discussed in this section. But it does say that they can be derived. I feel like if you could Google these, and you could actually Google this, and you could find the reduction formula, and you can find the table associated with this product of cotangent and cosecant. And I wanted to show you that, but we just proved one without a reduction formula, an alternative way. So I didn't look up a reduction formula. They didn't give me a reduction formula, but I used an alternative way to come up with the blue box special. So once again, the table they give is for products of secant and tangent, or tangent times secant. They don't have a table for cotangent times cosecant. One table can be derived, or you could Google one and find a table. There are reduction formulas given for powers of tangent and secant. They do not give reduction formulas for powers of cotangent and cosecant, but there are formulas out there for those, just not in this particular textbook or this insert. The last one, the antiderivative of cosecant u du, I will show you the proof of that. It's very similar to when we proved the blue box special for just secant in the last video. So we proved this blue box in the last video. We proved this blue box in the last video. So now I want to show you the proof for this blue box special for plain old just cosecant u. The proof of that, we're going to do something very similar to the other when we integrated just secant. Now we're integrating cosecant. Here is your blue box formula. What you do is you multiply by a form of 1, and that's cosecant x minus cotangent x over cosecant x minus cotangent x. And then you distribute cosecant x times cosecant x is cosecant squared. Cosecant x times negative cotangent x is negative cosecant x cotangent x, all divided by cosecant x minus cotangent x. Let u be the entire denominator, and by your Calculus 1 days, you're supposed to have memorized the derivative of cosecant is negative cosecant x cotangent x. The derivative of cotangent by itself is negative cosecant squared, but we are subtracting that. So minus a negative cosecant squared. And if you change that to positive or plus cosecant squared, this becomes cosecant squared x minus or plus a negative cosecant x cotangent x, which the reason you want to rewrite that is you want to be able to see that that is your numerator. Cosecant squared x minus cosecant x cotangent x. Thereby, this easily becomes 1 over u du, and that's natural log absolute value of u. And what was u? Cosecant x minus cotangent x. So there's your blue box formula for this. Now, that concludes the part of the lecture where I want to derive and work on proving some of the blue box specials. I think and I pray, I hope and pray that you do have the concept that I wanted to prove some of them. I don't feel like I would be completely explaining, I would not be able to explain the section and be complete if I didn't show you how they derived some of these formulas. Again, what I'm hoping that you'll be able to do on quizzes and tests is to take, for example, the antiderivative of cosecant of 6x minus 5. And then you would let u be 6x minus 5. Du equals 6 dx. So you would put a 1 over 6 on the outside and a 6 on the inside and change this over to u. so that you can go to a blue box special. And again, you're going to have to know where to find these. There's your blue box special. So according to my blue box special, this is going to be 1 over 6 natural log absolute value of cosecant u minus cotangent u plus c. Again, there's the blue box. Then I have to go back to x. So this is going to be cosecant of 6x minus 5 minus cotangent of 6x minus 5 plus c. And that's how simple it can be. You don't have to derive the formula for cosecant u. You could just look it up as a blue box special or a formula and then go from there and give your final answer for this particular problem. Now, I am going to visit each Roman numeral and give an example in this video. That means that I'm going to give, going back to the lecture handout, if I really want to be thorough, I need to give an example of power of sine and cosine, product of sine and cosine, 2 examples because it works 2 different ways or 2 types of problems. I need to give an example of a power of tangent and secant. I need to give an example of a product of tangent and secant, which involves a table. And then I need to work an example with an alternative method. Now, these problems you can actually work on inside of class, or on your own, and here are the answers. If you notice, problem 1 is a power of cosine problem. Problem 2 is a product of sine and cosine, which is going to need a table. And you better rewrite this to put sine first. Sine of 6x quantity cubed goes before cosine of 6x quantity squared in standard form to use the table. Problem number 3 in your lecture handout. That is this particular type of problem, a power of tangent or secant. Well, I chose a power of, excuse me, I think I skipped a problem. Oh, problem number 2 is 2 problems. This one involves the table, products of sine and cosine. Here's the other part B, problem 2, products of sine and cosine, where you use the trig identity, and the answer is 7 over 24. Problem 3 is Roman numeral number 3, a power of secant, and here's the answer. Problem 4 is u sub once or twice, but that is going to be products of tangent and secant, where you use a table. I think tangent's supposed to come first to be in standard form, so you'll have to rewrite this so that tangent cubed comes before secant to the 5th power. And then an alternative method for powers of cosine. So I have a cosine cubed, which we have a blue box special for cosine cubed, but we're going to use an alternative method to come up with that blue box special there for that problem. So that gives you wonderful examples, but I am going to show you different examples on the video, and the main reason why is because I feel like you need more examples. More examples will help you. So here we go. I'm going to start with just some blank paper. Again, you do not have these problems in your handout. Here is an example of a power of sine and cosine. Okay, sorry about the delay. Let's do sine of x plus 4 to the 4th power. You will do u sub and this becomes sine of u to the 4th power. Because u was x plus 4, I did not have to multiply the inside by any type of scalar and its reciprocal or any type of form of 1. Du equals dx. Then you go to your formula sheet and there is already a formula for sine to the 4th power. Now on your test, if I ask you to give me this formula, it's not in terms of u. You will cut and paste glue stick and give me the formula in terms of x. But when you use the formula in showing your work, you better put u in place of x. So for example, if I ask you for part A formula, it is perfectly okay. You should write down what they have here. Sine of x to the 4th power. That's 1/8 x minus 1/2 sine of 2x plus 1/32 sine of 4x. Plus c. So that's the blue box special. So 1/8 times x minus 1/4 times sine of 2x plus 1/32 sine of 4x plus c. I do enjoy the parentheses around the 2x and the 4x. Now, when you show the work for the problem, I've just proven that sine of x plus 4 to the 4th power is equal to sine of u to the 4th power. And we're ready for the blue box special. That's going to be 1/8 times u minus 1/4 sine of 2u plus 1/32 sine of 4u plus c. Hope you see that even though the formula is in terms of x, because we changed our problem to have variable u, and we have to do that, that when we do give our blue box special, it has to be in terms of variable u. So 1/8 u minus 1/4 sine of 2u plus 1/32 sine of 4 times u. Then you go back and say, well, that's 1/8 times x plus 4 minus 1/4 sine of 2 times x plus 4 plus 1/32 sine of 4 times x plus 4 plus c. And you do want to kind of multiply everything out and collect like terms as if possible. And so that would be 1/8 times x plus 1/8 times 4 if you distribute the 1/8 minus 1/4 sine. And I'm just going to say that's 2x plus 8 plus 1/32 sine of 4x plus 16 plus c. And I see that this 1/8 plus 4 is going to become 1/2. So I'm going to say plus 1/2 here at the end of the problem instead of here. 1/4 sine of 2x plus 8 plus 1 over 32 sine of 4x plus 16 plus 1/2 plus c. And this is where you may decide, like I'm about to do, go back, and because you can collect these two, go back now that you can see that clearly and make that a c sub 1 throughout the problem, so that you can say 1/2 plus c sub 1 is plus an overall c in your final answer. And there's your final answer for that problem. Again, a very simple problem to change over to u, and then you state its blue box special, and then you go back to x. U is x plus 4, and so I distributed the 1 over 8. I distributed the 2. I distributed the 4. And then I realized closer to the end I was going to need to make these c sub 1s. You don't really realize that until you find out that in simplifying this, you have a number like 1/2. 1/8 times 4 is 1/2. Then you realize you're going to have to add those two terms together and collect like terms and make it a c sub 1 instead. So this should be your final answer if no mistakes have been made. Okay, so that was one problem from Roman numeral number 1, a power of sine. Now I'm going to show you a problem number 2, which comes from Roman numeral number 2, a product of sine and cosine, and we're going to use a table. The one that I would like for us to do together is sine of 2x to the 4th, cosine of 2x to the 5th. Sine of 2x to the 4th times cosine of 2x to the 5th. The first thing you'll do is you'll do u sub. So you will need a 1/2 on the outside, and a 2 on the inside. When you change over to u, it is sine of u to the 4th times cosine of u to the 5th. And now you can utilize your table. You have to notice that the power of sine is even and the power of cosine is odd to use the table. Going to the table, we're going to follow these rules. So, did we have the situation where n was odd? Yes. Did we have the situation where m is odd? No, because it was sine to the 4th and cosine to the 5th. Did we have the situation where both are even? So obviously for this problem, we have to follow these bullets. Split off a factor of cosine. Apply the relevant identity that cosine squared is 1 minus sine squared. And make another round of u sub that u is equal to sine x. So I'm going to follow these bullets. The first thing I'm going to do is split off a factor of cosine. Splitting off a factor of cosine would be sine of u to the 4th times cosine of u to the 4th times cosine of u. So, and this is all multiplication. And I still haven't changed the problem. It says apply the relevant identity that cosine squared is 1 minus sine squared. So this is what we're going to do. In order to see cosine squared, we are going to have to write that as cosine squared u quantity squared. Again, I still haven't changed the problem from the original problem above, which is sine of 2x to the 4th times cosine of 2x to the 5th. This is going to be cosine to the 4th times cosine is cosine to the 5th. For cosine squared, it said use the identity or Pythagorean identity. And that's going to be 1 minus sine squared u quantity squared times cosine u du. You can FOIL this out, but I feel like it's wiser to go ahead and do the u sub that they tell you to do before you FOIL and multiply everything out. Because that could be a lot of algebra there. So what they said to do with the third bullet, make the substitution that u is sine x. So we're going to do that. I'm going to do that, and of course I'll have boxes off to the side. What I should have done, and you'll have to forgive me, instead of doing what they said by table, I'm already in u, so I'll have to let w equal sine u, because technically that's the second round of u sub for the problem. Thereby dw is cosine of u du. And guess what? Cosine of u du is dw. This becomes 1/2 w to the 4th 1 minus w squared quantity squared dw. So wherever you see sine, you want to replace it with w. Then we're going to FOIL and collect like terms and find the antiderivative. FOILing this is going to be first terms, outer terms, inner terms, last terms. The first terms will be 1 times 1. The outer terms will be negative w squared. The inner terms, negative w squared. And the last terms plus w to the 4th. Then I distribute w to the 4th to all of these. So that's w to the 4th minus, well, to be honest, you could collect this and make this minus 2 w to the 2nd power. Collect like terms here. Since I missed that, what I'll do is I'll write it here. Please don't do this and do what I'm showing you here. That's minus 2w squared. So w to the 4th times a negative 2w squared is minus 2. W, like bases, add exponents. 4 plus 2 is 6. And then w to the 4th times w to the 4th is going to be w to the 8th power. We know the antiderivative through the power rule. Watch this. Here we go. 1/5 w to the 5th minus 2w to the 7th over 7 plus w to the 8th, or excuse me, w to the 9th over 9 plus an overall c. Remember, if you were to take the derivative of this, 1/5 w to the 5th, you would get w to the 4th back. The derivative of 2/7 or negative 2/7 w to the 7th power, you should get negative 2w to the 6th power back. And the derivative of 1/9 w to the 9th power, you should get w to the 8th power back. Now, the last thing we've got to do is go back to u and then go back to x. because our final answer has to be in x because we started in x. This is going to be 1 over 10 sine of u to the 5th power minus, so 1/2 times 1 over 5 is 1 over 10. 1/2 times a negative 2/7. Looks like the 2's would cancel. And that would be minus 1 over 7 sine of u to the 7th power plus 1 over 18 sine of u to the 9th power. And then u was 2x. So 1/10 sine of 2x to the 5th minus 1 over 7 sine of 2x to the 7th plus 1 over 18 sine of 2x to the 9th plus c. And there's your final answer for this problem. And again, we followed the bullets. So 1/5 sine of 2x to the 5th minus 1/7 sine of 2x to the 7th power plus, I read this incorrectly, 1/10 sine of 2x to the 5th minus 1/7 sine of 2x to the 7th plus 1 over 18 sine of 2x to the 9th. And I'll tell you why I read that incorrectly. In your insert, I made this particular example from this one. This insert shows you how to do sine of x to the 4th times cosine x to the 5th. I made it a little bit more difficult of a problem by making it sine of 2x to the 4th times cosine of 2x to the 5th. So when I was looking on the other side here, when it's just sine of x to the 4th and cosine of x to the 5th, they have 1/5 sine of x to the 5th minus 2/7 sine of x to the 7th plus 1/9 sine of x to the 9th plus c. But if you're thinking about my result, I have to multiply all of these coefficients by 1/2. So that's 1 over 10. That becomes minus 1 over 7, and that becomes positive 1 over 18. And all of these arguments, x, would be 2x. So I am correct in my final answer. I made my problem a little bit more complicated, but this is my correct answer for the problem by making it just a little bit more complicated, which required u sub twice. Okay, that was the second problem. Now, for the second problem, I guess you would call this part B. I want to show a problem where you have a product of sine and cosine. You don't use the table, but you use the trig identities. And the problem that I'd like to show you is sine of 7x cosine of 3x. Now, this comes into the formula for sine of mx cosine of nx dx. So m is 7 and n is 3. If we go, to our formula sheet and we go to the identities, we need to rewrite by using sine alpha cosine beta as 1/2 sine of alpha minus beta plus sine of alpha plus beta. And that's the identity, so we're going to rewrite the integrand. In this case, alpha is 7x and beta is 3x, if you want to think of it that way. I'm also going to write the identity down. sine of alpha cosine of beta is 1/2 sine of alpha minus beta plus sine of alpha plus beta. And that again is coming from here. Okay. Then I'm going to rewrite my integrand. Let me draw a line. And I'm going to replace this with 1/2 sine of 7x minus 3x plus sine of 7x plus 3x using my identity. Alpha is 7x, beta is 3x. The 1/2 I'm going to bring on the outside, and I'm going to make that sine of 4x as it is, plus the sine of 10x. What is highly recommended at this stage is that you do 2 different rounds of u sub. U is 4x, w is 10x, or you could just break it up into 2 indefinite integrals. But make sure you say the 1/2 applies to both of those indefinite integrals, not just one of them. And I'll continue over here. If u is 4x, then du equals 4 dx. If w is 10x, then dw is equal to 10 dx. That means that you will need to put in some coefficients and see, looking for another color of pen. I think I'll make life easier. And I'm going to put that 4 here and that 1/4 here, the 10 here, and the 1/10 here. So I don't have to write down the next step. And I did use a different color. So that's 1/8 sine of u du plus 1/20 sine of w dw. The antiderivative of sine is negative cosine. Negative 1/8 cosine of u minus 1/20 cosine of w plus c. Then lastly, go back to x. U was 4x. So that's cosine and w was 10x. And there's your final answer for this problem. I think those types of problems involving those identities with alpha and beta are very simple problems. I cannot imagine you having a difficult time with those types of problems. Now that covers Roman numeral number 2, and I did the 2 different ways you can take a product of sine and cosine. The one way by table and the one way that involved trig identity. Okay, third Roman numeral is going to be a power of tangent and secant. And the one that I want to show you is, so I'll write down number 3. Let's do bear with me. I'm hoping I can make this work. Let's do tangent of 5x squared. So I guess I'm kind of making this easy. And I need to do an example of a definite integral. Let's do this as an indefinite first. U is 5x, du is 5 dx. So your next step is a 1/5 tangent of 5x quantity squared times 5 dx, which is 1/5 tangent of u quantity squared du. And then you go to your blue box formula for tangent squared. We don't have to use the reduction formula to derive it. And the blue box formula for tangent squared is tangent x minus x plus c. Now I can write that formula down, cut, paste, glue, stick. If I ask you for the formula, it has to be in x just like the formula sheet. But to use it, I got to write down tangent of u minus u plus c. So I'm going to do that here. And I started to put the plus c on the inside of the brackets. If you do that, that's okay. But if you put the c on the inside of the brackets, make it plus c sub 1, and then 1/5 times c sub 1 in the very end is going to be an overall plus c. I went ahead and said plus c outside of the brackets. And then your final answer would be 1/5 tangent of 5x minus 1/5 times 5x plus c. So this is 1/5 tangent of 5x minus x plus c for your final answer as an indefinite integral. And again, that comes from this formula for tangent squared, tangent of x minus x plus c. But I use u instead. And then u is 5x. And I had to distribute the 1/5 to both of these. So 1/5 times 5x is just x. Final answer. Okay. Next question, number 4. We have to work on Roman numeral number 4, and that's going to be products of tangent and secant. So the one that I think that I will use, and it involves a chart, will be the antiderivative of tangent x. Let's do 3x quantity cubed, secant of 3x quantity cubed. You would have to do your u sub first. So u is 3x and du equals 3 dx. And obviously you know you put a 1/3 on the outside. And then a 3 dx here, 3 times dx, so that you can change that over to u. Once you change it to tangent u cubed times secant of u cubed, you're ready for the table because you're in standard form. The table from the formula sheet is on the first page. And it looks like, according to the table, both m and n are 3, so both are odd. The only one we can go to is the case where m is odd. 3 and 3 both are odd, so we have to go here. Split off a factor of secant times tangent. Apply the relevant identity that tangent squared is secant squared minus 1. Make the substitution that u is secant x. Okay? So we're going to follow the bullets. We're going to follow the bullets in terms of u. So it says split off a factor of secant x tangent x, but we're going to split off a factor of secant u tangent u instead. Sorry about squeezing the du in there at the end. Apply the relevant identity that secant squared is, tangent squared is secant squared minus 1. Be very careful, parentheses. Tangent squared is secant squared u minus 1 times secant squared u, because it didn't say to do anything with that, times secant u tangent u du. Then it said do another round of u sub and let u be secant x, but we're going to let w be secant u. And the derivative dw du is secant u tangent u. So when you cross multiply, dw is secant u tangent u du. And we already have that here. So you can go ahead and multiply everything out, but I'm going to change over to w. W squared minus 1 times w squared dw. So w is secant u. Then you'll have to distribute the w squared, and that's going to be w to the 4th minus w squared. The antiderivative is going to be 1/5 w to the 5th minus 1/3 w cubed plus an overall c. And then you've got to go all the way back to x. So I've got to go back to u first. 1/3, 1/5 secant of u to the 5th power minus 1/3 secant of u to the 3rd power plus c. I think in the next step I'll go ahead and distribute the 1/3 to both of those, and at the same time I'll substitute in for u, and u was originally 3x, so that's 1/15 secant of 3x to the 5th power minus 1/9 secant of 3x cubed plus c. So there's your final answer for the problem all the way back in x. And I just followed the table. Okay. So that was dealing with the product of tangent and secant and using a table. Okay. Final answer. And then we want to get into some alternatives. So I might show you more than one example of alternative methods. Remember, this is alternative methods for those powers of sine to the power of n, cosine to the power of n, tangent to the power of n, and secant to the power of n. Alternative methods. Before, they gave us reduction formulas for sine to the power of n, cosine to the power of n, tangent to the power of n, and secant. The first example with the alternative method is this one. I guess I better use some letters now. There is a blue box special for tangent squared. And if you go to the formula sheet, they say, and we used this in this video already, that it's tangent x minus x plus c. You can use the reduction formula to derive that by putting in n equals 2. And I can do that, and I probably should do that first. But that's really not alternative method. Then I can show you what they mean by alternative method that helps you to avoid this particular reduction formula. So let me write down the reduction formula. It is equal to tangent of x to the n minus 1 over n minus 1 minus the antiderivative of tangent x to the n minus 2 dx. And so if n is 2, that's going to be tangent of x to the power of 2 minus 1 over 2 minus 1 minus the antiderivative of tangent to the 2 minus 2. This is going to just be tangent x over 1, or tangent x. This is going to be minus the antiderivative of tangent x to the 0 power, which is an understood 1. So this is tangent x minus x plus c. And there's your blue box special using the reduction formula. Now I'll show you the alternative. So the alternate way that helps you to avoid the reduction formula is to take tangent squared and rewrite it with secant squared x minus 1, because they are equivalent by the Pythagorean identity. Then you could break it up into secant squared x dx minus the antiderivative of 1 with respect to x. This is from Calculus 1. The antiderivative of secant squared, there's nothing to prove, is tangent x. The antiderivative of 1 is x. Therefore, using the Pythagorean identity, the reduction formula was not needed. So that's an alternative method. On a test, I would not ask you something as simple as tangent squared. It's already a blue box special. So on a test, I would have to ask you for something more complicated, like tangent of 3x plus 1 quantity squared. So you would do your u sub first. Once you changed it over to u, you go to your blue box formula, which is tangent u minus u plus c. And then you'd have to go all the way back to x because u is 3x plus 1. So it's the same technique as usual. I'll show you quickly. I'll even be so quick as to put a 3 on the inside and a 1/3 on the outside with a different color. And that's going to be 1/3 tangent squared u du, which blue box special, notice how I put the overall plus c on the outside, is tangent u minus u. Do not put tangent x minus x. And you can distribute the 1/3. 1/3 tangent of u So I distributed the 1/3 to both of them, and I went ahead and said u was the 3x plus 1. So your final answer, oh no, it looks like I'm going to have to do this. I didn't realize it until I'm looking at what I'm going to have to do to simplify. That's going to be negative 1/3 times 3x is going to be minus x minus 1/3 plus c sub 1. So we would have to say 1/3 tangent of 3x plus 1 minus x, and watch this, plus an overall c. if C sub 1 is any real number, and if you add a negative 1/3 to it, it's still any real number plus overall C. Final answer. So that's going to conclude this video. Again, what you need to do and what you will be doing with me in class, we will be working within the lecture packet, and we're going to have these particular problems that you could see on a test. Finally, the video, I didn't show a definite integral, but I show a definite integral here in the actual lecture packet. Thank you so much for taking the time to watch this particular video. It was a little bit longer than the first one, but I wanted to show you quite a few examples of how to use the blue box specials and how to use the tables and how to answer all the different problems that involve the 5 Roman numerals. Thank you very much, and I will see you in class.